We're continuing with Chapter 4, Reactions in Aqueous Solutions. So we've talked about precipitation reactions and acid-base reactions. In this video, we're going to talk about oxidation-reduction reactions. Okay, whereas acid-base reactions can be characterized as proton transfer processes, the class of reactions called oxidation-reduction or redox reactions are considered electron transfer reactions. Oxidation-reduction reactions are very much a part of the world around us. They range from the burning of fossil fuels to the action of household bleach. Additionally, most metallic and nonmetallic elements are obtained from their ores by the process of oxidation or reduction. So yes, of all of the reactions that occur in nature, biological processes, industrial processes, etc., many of these reactions are oxidation-reduction reactions, redox reactions. So, like they just mentioned, the burning of fossil fuels. Any combustion process involves a redox reaction. It mentioned here, most metallic and nonmetallic elements are obtained from their ores by the process of redox reaction. So, for example, we mine iron oxides from the earth and obtain iron ores like Fe2O3, Fe3O4, FeO. Pure iron is obtained from these oxides using oxidation-reduction reactions. But all of the reactions we've studied up to this point, so the precipitation and acid-base reactions, none of these have been redox reactions. So then, okay, what exactly is a redox reaction? Well, as just mentioned, it's a reaction that involves the transfer of electrons. And by a transfer of electrons, what they're referring to is, so if you would examine all of the reactant compounds of a chemical reaction, looking at the different atoms associated with each element, you would see a certain number of electrons associated with those atoms. So either electrons directly around the nucleus in the atom electron cloud, or perhaps there's some of the outer electrons are only partially associated with the atom. But still, there's this like total number of electrons associated with each of the atoms of the different compounds, the reactant compounds. Okay, but if you compare these numbers of electrons of the atoms of the reactant compounds with the number of electrons of those same atoms in the product compounds, for a redox reaction, you're going to see a change in the numbers of these associated electrons. Okay, so many important redox reactions take place in water, but not all redox reactions occur in aqueous solution. So yes, not all redox reactions occur in aqueous solution. And it's really the same idea with precipitation and acid-base reactions. It's not like those reactions are restricted to occurring in aqueous solution. You can think about how an acid-base reaction would be any chemical reaction occurring in any type of system where a proton is transferred from one substance to another substance. That's it. It doesn't necessarily have to have anything to do with aqueous solution. Okay, in a reaction with precipitation type character, you can think about would be something like any reaction in any circumstance in which a gas or liquid reactant transforms into a solid. Okay, but of all of the reactions in nature, biological processes, etc., that do occur in aqueous solution, these are three of the primary ones: the precipitation, acid, base, and oxidation reduction. So that's why we're studying them here in this chapter. Okay, but we're going to start by looking at a redox reaction that does not occur in aqueous solution. So consider the formation of magnesium oxide from magnesium and oxygen. So we've got this solid magnesium in an O2 gas environment transforms into magnesium oxide, the ionic compound magnesium oxide. And so you can see this is clearly not a reaction in aqueous solution. We don't have any substances that are in the aqueous phase, right? Nothing is dissolved in water here. Okay, and so if we look here, again, this reaction is not occurring in aqueous solution. So we've got solid magnesium in an O2 gas environment. And so the O2 gas molecules are going to be flying everywhere with some crashing into the surface of the magnesium. Okay, and so at the right conditions of temperature and pressure, so in this case, you could think about at atmospheric pressure and higher temperature, higher than room temperature conditions, when like an O2 molecule crashes into the surface of the magnesium, it's going to be energetically favorable for a chemical reaction to take place. So atoms to rearrange themselves and form new bonds, to where what results is this solid magnesium oxide ionic compound. Okay, and you can also see an example here of this reaction has a precipitation type character, in the sense that you've got this gas phase coming, molecules coming out of the gas phase into a solid phase, right? Okay, so the chemical equation, we know that for this chemical reaction, we have solid magnesium, O2 gas, and what results is magnesium oxide. So we know this. It's not like for some of the problems in the previous chapter, like determining empirical formulas, we didn't know the entire composition of the compounds. No, we know what reactants and products are present. So we write all the reactants, we write the products, and then we balance the equation. And so here's the resulting chemical equation for this chemical reaction. Now, okay, what we want to do is, and this is what you would in general do for any chemical reaction, is we want to analyze the oxidation reduction properties of the reaction. So first, is it a redox reaction? And then if it is, which compounds or elements are involved in the electron transfer process? How many electrons are transferred or shifted, etc.? Okay, the most efficient way to do this analysis is using oxidation numbers. But we haven't talked about oxidation numbers yet. We'll discuss them in the next video. Here, we're just going to analyze the redox properties of this reaction manually. Okay, so if we examine the reactants, we've got neutral magnesium atoms and neutral oxygen atoms. So it's neutral. You have neutral oxygen atoms because, okay, you have O2, but each oxygen atom in the O2 molecule is neutral, right? So that's what's on the reactant side. You've got a single O2 molecule and then two magnesium atoms. Okay, now on the right side, we've got 2 units of magnesium oxide. But we know what magnesium oxide is. It's an ionic compound made up of bonds between magnesium 2+ cations and O2- anions. Okay, so we can clearly see here that electrons are transferred in this reaction, because we started with these neutral magnesium atoms and oxygen atoms, and then we ended with magnesium atoms to where their associated electrons was 2 less than neutral, and oxygen atoms where the associated electrons were 2 more than neutral. Okay, and specifically what happened is you have, so, okay, well, this is, you have 2 magnesium 2 pluses and 2 O2 minuses, right, with the coefficient 2. So what occurred is that you have these 2 magnesium atoms, okay, and you have the single O2 molecule, so the O2 molecule breaks up, and each magnesium atom donates 2 electrons to an oxygen atom. And so that's how you get 2 Mg2 pluses and 2 O2 minuses. Okay, now, just to give you an example of this same kind of analysis for a precipitation reaction, so here is the net ionic equation for a precipitation reaction resulting from the mixing of aqueous solutions of lead 2 nitrate and potassium iodide. Okay, the net result is that you've got lead 2+ ions in solution, iodide ions in solution, and those interact to precipitate out and form the ionic compound solid lead 2 iodide. Okay, but if we analyze, so the reactants, we have lead 2+ and I-, but in the products, so lead 2 iodide, well, this is just a bonding of lead 2+ and I- ions, right? And so we can see there's been no transfer of electrons in this reaction. We started with lead 2 plus and I minus, and we ended with lead 2 plus and I minus. So this is not a redox reaction. The precipitation reactions we analyzed were not redox reactions. And if we did the same kind of analysis with any of the acid-base neutralization reactions we analyzed, we would see the same result, that those were not redox reactions. Okay, and so once we've identified that a particular reaction is a redox reaction, what we can do next is we can construct what are called the half reactions. So half reactions apply to redox reactions, just to redox reactions, and they're helpful for analyzing the electron transfer process in the reaction. So now first note that the half reactions are different from the ionic and net ionic equations. The ionic and net ionic equations only apply to reactions in solution, where substances dissolve and dissociate into ions. Now, this particular reaction that we're looking at here isn't occurring in aqueous solution, so there's no ionic or net ionic equations to construct, but we're about to look at some reactions in a second, some redox reactions in aqueous solution, and so we're going to construct the ionic and net ionic equations. Any reaction in aqueous solution involving ions, no matter what kind of reaction it is, you can construct the ionic and net ionic equations. Okay, but again, the half reactions are separate from the ionic and net ionic equations, and they just apply to redox reactions. So for any redox reaction, you can construct the half reactions, and so we're going to also construct these half reactions for the redox reactions in aqueous solution. You can construct both the ionic and net ionic equations and the half reactions because they have two different purposes. Again, the half reactions are for analyzing the specifics, the details of the electron transfer process in the redox reaction, whereas, as we have discussed before, the ionic and net ionic equations are more about demonstrating the physical reality of the chemical reaction with respect to the ions dissolved in solution. Okay, and so we're going to see in a second how the half reactions aren't really helpful as far as demonstrating some sort of physical reality in the same sense as the ionic and net ionic equations, as they are more for just clearly showing the electron transfer process in terms of how many electrons were transferred, from which elements to which elements, and what were the starting and ending compounds. Okay, so let's construct the half reactions for this redox reaction. The first half reaction is going to be based on the reactant that's going to be losing electrons. So for the half reactions, we're going to go to the main chemical equation, look at all of the reactants. There could be more than two. Okay, whatever reactant is associated with the loss of electrons, that reactant is going to go on the reactant side of the first half reaction. And then the other reactant, there's going to be a second reactant that's associated with the gain of electrons. That reactant's going to be on the reactant side of the second half reaction. Okay, so what we do is we know that magnesium loses electrons here, so we just take the full magnesium, this full compound here, whatever the exact chemical formula is with the corresponding coefficient, just like it is, and we put that here on the reactant side of the first half reaction. Okay, and then we could go ahead and do the same thing for the reactant that's associated with the gaining of electrons for the second half reaction. Just take the exact chemical formula of this reactant as it is with its coefficient and put it here on the reactant side of this second reaction. Okay, so now for the first half reaction, the reactant is going to be, like we can think about splitting up with the electrons it's going to be losing. Okay, so what we do is we say this transforms into, okay, but now what do we put here? Okay, well, we reference our analysis of the product side of the main chemical reaction. We know that 2Mg2 plus is produced and 2O2 minus is produced. So this is going to split up into 2 Mg2 pluses with each Mg giving up 2 electrons, so plus 4 electrons, right? So we can check, do the elements balance? You have 2 magnesiums on each side. And does the charge balance? You've got neutral here, plus 4, minus 4, neutral here on the product side. And we want the charge to balance because there's no like law of conservation of charge. The charge balance is just like an offshoot of the law of conservation of mass. Because if the charge doesn't balance, then that would suggest that there's electrons appearing into the system or disappearing from the system, right? And electrons are mass. Okay, now for the second half reaction, we're starting with this O2 reactant. This O2 is going to accept the electrons that were given up by the magnesium. It's going to accept these 4 electrons, right? So we're going to put these 4 electrons here. And so now, okay, when the O2 combines with the 4 electrons, you put this arrow here to go to the product side. Well, okay, what's the result? Well, we saw here there's going to be 2 O2 minuses. Okay, and then once again, you have 2 oxygens, -4 on the left, -4 on the right, so the mass and the charge balances. Okay, and so that's the half reactions. You can see they're just clearly showing you which reactants are involved in the redox process. How many electrons are transferred from and to these reactants and the resulting species that is formed in the products. How many electrons are transferred to and from these reactants and the resulting species formed in the products. Okay, so now we can go ahead and add these 2 half reactions. So you have taken together all of the reactants on this side of the added chemical reaction and all the products on this side. Okay, but now we can cancel these 4 electrons here. They occur on both sides as intermediate species. Now, and that's what they do next, and here's the updated equation. Now, note that these intermediate species are different from spectator ions. So we also canceled spectator ions, right? But this is different because we didn't get the ionic equation by like adding chemical reactions. This here is the result of adding chemical reactions. And the idea is when you're adding chemical reactions, these are called half reactions because they're occurring in sequence. You've got these magnesium atoms lose 4 electrons, and then those 4 electrons, one of these products is the reactant in the second reaction, right? These are the same 4 electrons. These reactions are coupled together. And so intermediate species are they're actually taking part in the chemical reaction as opposed to spectator ions. But they're intermediate. They're not part of the first initial reactants and the absolute final products. So in the net chemical reaction, the intermediate species don't show up, right? So just know this is different. This is functionally different from what spectator ions are. Spectator ions aren't taking part in the chemical reaction. That's why those cancel, whereas the intermediate species are taking part. Okay, so what this shows here, this gives you the overall picture with the 2 half reactions added together. You're starting with 2 magnesium atoms and a single O2 molecule, and you're ending with 2 magnesium 2+ cations and 2 O2- anions. That's the electron transfer process, right? This is everything balances. The magnesium's balanced, the oxygen's balanced, the charge balances. This is the overall electron transfer process. But this equation is kind of useful because you can also see how many electrons are transferred. Okay, but now in reality, though, it's not like you've got some ions floating around in the system like would be the case with aqueous solution, right? Really, these 2 species are going to pretty much right away combine and form the ionic compound, right? So they come together like this. You go from here, these combine to form the 2 units of magnesium oxide, right? So you can see how the half reactions aren't really reflective of like the physical reality of what's happening in the same way as the ionic and net ionic equations, because you don't have magnesium atoms disassociating from electrons, right? You don't have, these aren't like, this almost implies these are floating around in the system. I mean, when it comes to ions, I guess there is kind of a dissociation, a full transfer of electrons, but we're going to see we can construct these half reactions for redox reactions involving molecules, not ions. And you do it the same way, right? So, but with like molecules, it's not a full transfer of electrons. And so this is really all happening. None of these components here, these half reactions, if we come here, nothing is floating around in the system. It's all happening in this confined region here where the O2 molecule crashes into the magnesium surface, and it all kind of happens within that little confined region of contact. Okay. So now, the term oxidation reaction refers to the half reaction that involves loss of electrons, and the term reduction reaction is a half reaction that involves the gain of electrons. So they're saying that this first reaction is called, you call the oxidation reaction, and this second reaction you call the reduction half reaction. And so you can, another way you can use these terms, oxidation and reduction, is you can say that in this chemical reaction, the magnesium was oxidized and the oxygen was reduced. Now, as far as memorizing the terms oxidation and reduction, I've always found it kind of difficult. There's really no helpful mnemonics to try and memorize this. It's just like a brute force memorization you need to do, because, like, okay, why is it called reduction if you gain electrons? Well, it's because the charge is reduced, right? The charge is going down. If you start neutral and you gain 2 electrons here, then the charge has been reduced. Okay, now the term oxidation, it says chemists originally used oxidation to denote the combination of elements with oxygen. However, it now has a broader meaning that includes reactions not involving oxygen. So what they're saying is that you can think about how the original chemists were very familiar with oxides. There's a lot of oxides in nature. Many ionic compounds are oxides. And then when it comes to metals, a lot of metals exist in nature as oxides. Like we talked about with the iron oxide, right? Okay, but when you have something chemically reacting with oxygen this way, I mean, not even, it doesn't have to be an ionic compound, even with a molecular compound, oxygen is very electronegative. It's going to pull electrons towards it. So these substances like iron, etc., get oxidized. So chemists were familiar with oxygen causing the oxidation of other substances, causing other substances to you have chemical reactions and oxygen causes other substances to lose electrons. Okay, but now the term has a broader meaning that includes, so it's for any oxidation reduction reaction, any redox reaction, whatever element or elements lose electrons, those elements are said to be being oxidized in general. And same idea with reduction. In a redox reaction, whatever element or elements are gaining electrons, those elements are said to be being reduced. Okay, in the formation of magnesium oxide, the magnesium is oxidized. Yeah, it is said to act as a reducing agent because it donates electrons to oxygen and causes oxygen to be reduced. Oxygen, on the other hand, is reduced and acts as an oxidizing agent because it accepts electrons from magnesium, causing magnesium to be oxidized. So yeah, you might look at, when you see these terms, you might think, well, man, why these extra terms? Why make this so confusing? So now you have in a redox reaction, you have one substance that's oxidized, one's reduced, but then you could also refer to one of those substances as the reducing agent and the other as the oxidizing agent, to where the substance that's oxidized is the reducing agent. Just so confusing, right? Well, okay, this is useful because, so first, the principle we talked about with acid-base reactions, in that you can't have a Bronsted acid be present in a system without a Bronsted base also present. Like if a proton is going to be donated, there has to be something to accept the proton. You might say, well, no, what about like an empty space? Couldn't you have you have a proton donated in empty space and nothing accepts it? Well, no, because think about it. That would be like if you said, okay, you have some hydrogen chloride gas, right? Which you don't officially call that an acid until it's put into a system where it donates the proton. So you go into empty space, you've got some region of empty space, okay, and then you say, all right, you're going to put that acid into empty space. You're going to put the hydrogen chloride gas into empty space. Well, nothing's going to happen. It's not going to donate the proton. Why would it? Something needs to be present that's going to make it energetically favorable for it to give up that proton. And what's present is going to be a base. Okay, so again, you can't have a Bronsted acid without a Bronsted base and vice versa. And it's the same exact idea with redox reactions. There can't be oxidation without reduction. You can't lose electrons without something there to accept the electrons. Okay, and so because of that, you're thinking, okay, you have a substance in a redox reaction that's oxidized, and it's oxidized by a oxidizing agent. And then you have something that's reduced, and that's reduced by a reducing agent. And you can think about how this is useful from the sense that, with early chemists using the term oxidation to describe elements combined with oxygen, right? So these elements are oxidized. When they combine with oxygen in a chemical reaction, they're oxidized. So you can view oxygen as an oxidizing agent, right? You could say oxygen is a well-known oxidizing agent. It oxidizes other compounds. It oxidizes other elements, right? You can refer to substances or elements as, okay, are they oxidizing or reducing agents? So this can be a useful perspective to view the elements involved in redox reactions from the perspective of the agents of reduction and the agents of oxidation. What's causing the reduction to happen? What's causing the oxidation to happen? Okay. Note that the extent of oxidation in a redox reaction must be equal to the extent of reduction. That is, the number of electrons lost by a reducing agent must be equal to the number of electrons gained by an oxidizing agent. Yeah, so it wouldn't make any sense if the number of electrons that were lost by whatever's being oxidized in the redox reaction, that same number of electrons weren't gained by whatever's being reduced in the redox reaction, right? Otherwise, the charge wouldn't balance, which would make sense. Okay, so now let's take a look at a redox reaction that occurs in aqueous solution. So the occurrence of electron transfer is more apparent in some redox reactions than others. When metallic zinc is added to a solution containing copper 2 sulfate, zinc reduces copper 2 plus by donating 2 electrons to it. So, okay, here's this reaction in aqueous solution. So we know this is taking place in aqueous solution because we've got these certain substances in the aqueous phase, right? Now, but how is this reaction different than the reactions in aqueous solution we've studied so far? So the precipitation and the acid-base reactions. The difference is we have a non-aqueous solid component on the reactant side. Okay, but now for all the precipitation and acid-base reactions we've studied, all of the reactants were aqueous, right? Every reaction in aqueous solution we've studied so far, it was, you start with, right at the beginning, you've got ions dissolved in solution floating around everywhere, and they all get to interact, and a chemical reaction takes place as the result of some of those ions coming together and forming a chemical reaction, like a precipitate comes out, or maybe you've got hydrogen ions running into OH minus ions, and they form H2O. Okay, but this is different. So, like, yes, you could, so here's a precipitation reaction we analyzed. Okay, you see both of the reactants are aqueous. It's not like this couldn't have potentially taken place inside a beaker that has zinc in it, assuming that wouldn't affect the reaction, but let's say it doesn't. Yeah, so you could have a beaker of pure water, then you put a bar of zinc in it. Okay, then you add these solutions in and this reaction takes place. But if nothing happened with no reaction happened with the zinc, then you just end up with zinc on this side. So this would be a spectator species, and it just cancels. So the idea is for like the primary chemical reaction, if you ever presented with the main cover page main chemical equation for a chemical reaction, then whatever compounds are shown in the reaction, it's implied that they're involved in the chemical reaction, right? Those substances are going to be having some sort of action involved with chemical reaction. Okay, and so because of that, what's different here than what we've studied so far, the reactions in aqueous solution we've studied so far, is that we're going to have we have a solid bar of zinc, or solid zinc, in like pure water, right? Let's say we start with a pure beaker of water, we put some solid zinc in it, but it doesn't dissolve, nothing happens. All right, but when we add copper 2 sulfate to the solution, now apparently, we're going to see in a second, there's a chemical reaction is going to take place. So this is different because what this is suggesting is that you're going to have these copper 2 plus, this is aqueous, so you can have copper 2 plus and SO42 minus ions in the solution, and they're going to be mobile and just moving around everywhere, but some of these are going to crash into the surface of the solid zinc, and that's going to result in a chemical reaction, right? So you can see this is a little bit different than the reactions in aqueous solution we've looked at so far. Okay, and so what's going to result is we can see we're going to end up with zinc sulfate aqueous, so zinc 2 plus and SO42 minus ions in solution, and solid copper. So it looks like the copper 2 plus ions are going to come out of the solution and be replaced by zinc 2 plus ions, with the sulfates not doing anything chemically. And we can get a clear picture of this if, so this is a reaction in aqueous solution, right? It involves compounds breaking up into ions. So they construct the ionic and net ionic equations, and here's the net ionic equation for this chemical reaction, which again is giving you the most fully realistic physical picture of what's taking place in the solution, the chemical reaction that's taking place. And you've got solid zinc in this water environment with dissolved copper 2 plus ions in the water. These are interacting, these ions are crashing into the zinc, and as a result, zinc 2 plus ions are coming out to the solution, and the copper 2 plus ions are going into the solid state. And so now we can, once again, manually analyze this we're not using oxidation numbers yet to see, okay, well, is this a redox reaction? And it clearly is. We've got, in order for zinc 2 plus to go into the solution and copper 2 plus to come out as atomic copper, we're going to need to have 2 electrons transferred to these copper 2 plus ions, right? And so that's what happens. That's how you get zinc 2 plus and solid copper, right? So this is definitely a redox reaction. All right, so let's see. Here's an illustration. They've got a bar of zinc, and then it's this like blue tinted water. That's the copper ions. So initially you've got here's the copper 2 plus just ramming into the surface of the zinc, and then as a result you have electrons transferred, 2 electrons transferred from the zinc atoms to the copper. The copper comes into the solid state, and zinc 2 plus goes into the solution. And that's why it's starting to get a dark layer here, because the zinc is starting to come into the solution, and then over time you have that blue tint leaving, the copper anions, and a dark solution appearing. That's the zinc 2 plus in the solution. Okay, so now we can go ahead and construct the half reactions for this redox reaction. And for a redox reaction in aqueous solution, we're going to go ahead and reference the net ionic equation instead of the original equation. So, okay, the oxidation reaction, we're going to identify which of the reactants is losing electrons. Well, it's the zinc here, right? So let's just put a coefficient of 1. This is already balanced and everything. So there's the zinc, okay? And this is going to break up into what? Zinc 2 pluses. Okay, but to do this, it must separate from 2 electrons, right? Okay, so that's the oxidation half reaction. The reduction half reaction, we come back to the reactants in the original equation and identify, okay, which reactant, and identify, okay, which of these reactants is gaining electrons in the redox process. Well, that's going to be the copper 2 plus, right? And it's going to gain these 2 electrons. So copper 2 plus 2 electrons, and the result is going to be what? Copper. Just 1 unit of copper. So, okay, you have 1 zinc on each side. You have +2, -2. It's neutral on both sides. Here you've got +2, -2, 0, and then neutral on this side. So everything balances. Okay? So now we could analyze Here's another reaction in aqueous solution. You have solid copper and silver nitrate aqueous react to form copper 2 nitrate and solid silver. So this is the molecular equation, right? It's already balanced. You could just go through and break up any of the strong acids and bases, and you fully dissociate them into ions to make the ionic equation. Then you cancel the spectator ions, and what you're left with is the net ionic equation. And here's the net ionic equation. It's the solid copper is interacting with the dissolved silver ions, and when they interact, when silver crashes into the copper surface, it's similar to what we just saw. You have the electrons transferred from two electrons transferred from the copper to 2 silver cations to create 2 units of solid silver, right? So if we come here, here's a visual picture of this. So we're going to end up with copper in the solution. We're going to get that blue tint at the end of the reaction, but we start off with no blue tint in the solution. And then, but once you have the copper, the solid copper with the dissolved silver nitrate, but it's really more about the dissolved silver. The silver is interacting with the solid copper, and they sort of switch spots, right, with a transfer of electrons. That's why this is a redox reaction. You have electrons transferred between the ions and the neutral atoms. Okay, so we can go ahead and construct the half reactions. So which of these reactants is losing electrons? It's the copper, right? So we take the coefficient of 1 with the copper, its exact chemical formula, just copper. This is going to break up into what? Cu2 pluses. And then therefore there must be 2 electrons. All right, so the copper is balanced and the charge is balanced. +2, -2. All right, now which of these reactants are receiving these electrons? It's the silver ions, right? There's 2 silver cations. Is going to receive these 2 electrons. And the result is what? 2 units of silver, of atomic silver. And so 2 silver elements and +2, -2, neutral, and then it's neutral over here. Okay, so that's an overview of oxidation-reduction reactions, and also in particular oxidation-reduction reactions that occur in aqueous solution. Now, in the next video, we're going to talk about something that's also very important in regards to all oxidation-reduction reactions and occurring in aqueous solution or not, and that's oxidation numbers. And this is really important because the redox reactions that we just analyzed in this video, if you notice, they all involved ionic compounds. So let's see, we had magnesium oxide, right? Here we had copper 2 sulfate, zinc 2 sulfate. Here we had silver nitrate and copper 2 nitrate. Okay, so what you can think about is if you're dealing with a redox reaction that involves ionic compounds, the presence of ionic compounds can make it a lot easier to sort of like manually analyze the whole redox process as we were doing. So you're identifying which elements were oxidized, which were reduced, and then by how many electrons. Because we could go to the ionic compounds and identify, okay, this is composed of these ions, right? It's clear the ions that are made up of a certain ionic compound. Okay, but redox reactions don't have to involve ionic compounds like they're showing here. So you have H2 gas plus CO2 gas gives HCl gas. This is a redox reaction. And so is this. And there's no ionic compounds. But these are still definitely redox reactions because you don't need to have a full transfer of electrons from one element to another to have a redox reaction, which would be the case involving ions, right? That's ions. It's a full transfer of electrons. All you need is just a shifting of electrons from being associated with one element to being associated with another, right? So here we've got these neutral H2 molecules. So they've got their proton in the nucleus and their associated electron, right? They're neutral. But here in HCl, And like similar idea with in water, you've got that electron and the hydrogen pulled away from the hydrogen nucleus. So that change here, where you have neutral hydrogens in the reactants and then more positively skewed hydrogens in the products, that's a redox process. And so what oxidation numbers are going to allow us to do is, it's going to make it much easier we can be given any chemical reaction, and then we can go through and label all the atoms of the different elements in the chemical reaction with these oxidation numbers. And then we can compare oxidation numbers of reactants and products to see if any electron shifting has happened. So if it's a redox reaction, and then also to see to what extent the electron shifting happened, how many electrons were shifted, and corresponding to what elements were the electrons shifted.